let me open this up by asking you a question that's kind of a recap of stuff we did the other day. And so there's sort of two questions to kind of make the connection. So first of all, what is a neutron star? If you had to describe it, what is that object? Pulsars aside, what's a neutron star? Anybody can just unmute and jump in here. Go ahead, Fatini.
So a neutron star is, I don't remember exactly like the mass of the star that it originally was, but it's kind of like when you have a big star and then it dies and it starts like shedding off its outer layers or something. What's left is just a mass of neutrons, and it's really dense.
Okay, good. So it is the collapse. Okay, Judy.
It's like after the like supernova, something like that, and like it becomes like really dense and like really dense. So it becomes like a small value with like huge mass.
Good. So so a neutron star is the result of a collapsed core of a massive star that has died in a supernova explosion. Why do we think that the pulsar phenomenon, which is an observation of sort of a repeated signal in space, why do we think that neutron stars are responsible for this? What kinds of reasons do we have to suspect that? All right. Go ahead. Were you talking? No?
You kind of, your audio is messed up, so.
Oh, I'm sorry. Did it come through really loud all of a sudden?
Yeah.
I don't know why it does that. It occasionally does that. Okay. So my question, pardon me, was why do we think that neutron stars are responsible for the pulsar phenomenon of a repeated signal coming from space? Max.
Isn't it like what we think is that as the star, the original star dies through a supernova, it like starts to spin the material when it's like forming the neutron star, and that kind of spinning, we see like a pulsing light on Earth.
Okay, so stars do spin, and all of the star's features are kind of enhanced or emphasized or exaggerated once the star collapses. So if it was spinning slowly when it was younger, okay, after the collapse of the core, the spin rate goes up, the mass falls in, and this has to do with conservation of angular momentum, which isn't a topic that we touched on, but maybe somebody got to it in a presentation. I'm not sure. In your block, did anybody talk about conservation of angular momentum? I know we had some discussion of Magnus effect and things like that, spinning things, but anyway, we will explore this further. But it's kind of like when an ice skater pulls in their arms and they're spinning around and they spin faster, okay? So we need something that we know to be, or we expect to be spinning really fast, which we do expect neutron stars to do, but also the incredibly high density, that mass concentrated in a small radius, is sufficient to supply the necessary centripetal force to keep the thing together. Okay, so if pulsars are a repeating signal that's not from a flashing thing, it's got to be from a spinning thing, unless it's like aliens that are sending us signals, right? So the only thing that we know of that could spin this fast is something highly dense, because otherwise it would self-destruct. Just like if, oh, wait a minute, my door is blowing open and I don't want my cat to get out. Hang on a second. Yikes. Sorry, that was strange. The only thing that we know that could spin this fast and be this compact is the neutron star. And we saw a presentation, I think it was Eric and Justin were presenting on Tuesday when they were talking about pitching the ball or hitting the ball, and then the idea of spin and release. And so it's this concept that, you know, something is going so fast that you can't hang on to it anymore. Centripetal force is necessary and is provided by the neutron star. All right, so again, the pulsar has to be from some small, fast spinning, massive object, hence neutron star. All right, we also find them in supernova remnants, which is another reason we connect those dots. So what we're going to be thinking about today is how, the effects of being on the surface of such a thing. All right, how could we escape? How could a particle escape from such a thing? Or how could something be on the surface of it or orbit it? So instead of taking the approach from the angle of looking at centripetal force, what we're going to be looking at is approaching this question from the direction of conservation of energy. So last week I had you doing a conservation of energy lab with an elastic, and we were setting the kinetic energy equal to the potential energy that was stored in the elastic when it was stretched out. Today we're going to be thinking about, at least for starters, getting into orbit around an object and how those energy balances occur. And then we'll think about escaping from an orbit. So I'm going to switch over here, and this might cause weirdness with my audio, as it sometimes does, so just a warning, to drawing on a whiteboard. And Jack, I'll just let you know I'm having a problem with my surface that maybe you have an idea about, but I can't seem to get my surface detached from my keyboard. I don't know, I don't have a detach the keyboard option right now, so maybe you can help me out with that later. But right now I'm going to share my screen with you. Get back to Zoom here, share the screen, and you're going to be looking at a whiteboard in a second. All right, so do you guys see that where it says energy of orbits?
Yes.
Yeah.
Thank you. All right, so energy of orbits, we're going to do this in two cases. First for a particle of mass m, and then for a photon. And I'm going to shrink down this thumbnail video so that we don't see that on the screen there. All right, so let's think about a particle that is near the surface of a neutron star. So here's our neutron star, and our little particle of mass m is going around the neutron star. So it's in orbit just above the surface. I'm a little sloppy. Okay, so the particle has a mass of lowercase m, the neutron star has a mass of capital M, and it has a radius of r. And we're thinking about, like we did before, the idea of energy conservation. So conservation of energy for an orbit anyway, for a stable orbit for this item, its gravitational potential energy just above the surface there would be equal to its energy of motion, its kinetic energy. So this is like what you did with the elastic last week, where you set spring potential energy and kinetic energy equal. It's getting converted over, okay? So at the surface, or just above the surface, the gravitational potential energy, we know, is going to be the mass times lowercase g for this neutron star times the height that it is above the surface. And at the surface, it is at a height r, above the center, we'll say. And that's going to be set equal to 1/2 mv squared, where v is the speed that it has. And what we're interested in is figuring out the speed that something in orbit has to have to be stable, okay, would be equal to this value. And then anything above that, if it's going too fast, it'll go out of orbit and escape. Anything too slow, it would fall in if it wasn't at the surface, of course, right? If it's going to fall in, it's just going to fall to the ground, or to the neutron star, I guess. All right, what can we substitute in here for g? Well, actually, pardon, let's back up a second. What immediately cancels out from both sides of the equation? Shout it out. Mass. Thanks, Matthew. Okay. So the mass goes out. What do we do with that lowercase g for the surface of the neutron star based on our lesson earlier this week? Is there something we can substitute?
Is that gm divided by r squared?
Thank you, Judy. So yeah, GM divided by R squared. G is our gravitational constant, 6.67 times 10 to the minus 11. M is the mass of the neutron star, and then we have an R squared. So we can see what's going to happen over there on the left side is that we will have G, M, and then R at the top, R squared at the bottom, which is going to let us cancel out one of these R's, right? Equals 1/2 V squared. So if we solve this for the necessary speed, we will get the root of 2gm over r. So if we go exactly at this speed, we'll be in a stable orbit. If we go above that speed, we will escape. So sometimes this equation is called the escape velocity equation. The velocity necessary to escape. Now, what's interesting about this is that that checks the box for thinking about a particle of mass m. But if we're interested in thinking about what happens to a photon at the surface of a neutron star, things get very weird. And some of you might know, why would this be weird for a photon? What's going to be the problem here? For a photon, do you know? If we were to try to do the same calculation. Couple problems. What are we going for down here? We're looking at what is a necessary velocity for something to happen. But do you know anything about photons, particles of light, and their velocity?
Is it just that they always have the same velocity?
Constant, right? Why isn't this writing on me? Constant speed. Yeah, photons travel at the speed of light, so there's no changing it. And the other problem with photons is that they have no mass. Okay, so our calculation is going to be a little different for the photons. No mass, and they move at constant speed. So let's look at what has to change if a photon is to leave the surface of a neutron star. So a photon leaving the surface of a neutron star will also conserve energy. It has to. That's a law in physics. We have to conserve energy. Not allowed to not do that. So when the photon is on the surface, it has two kinds of energy. It has kinetic energy and potential energy. And once it leaves the surface and it's at a distance of infinity, it just has kinetic energy. So if we're thinking about conservation laws, we always do the energy before equals the energy after something happens. So we're going to think about it as being on the surface, and then the after condition being at a distance of infinity, all right, at infinity away. So it's totally escaped the gravitational pull of the neutron star. So when it's on the surface, a photon, because it's moving around, is unlike a regular particle that's in orbit. It has some initial KE, right? It's moving, plus potential energy, and that's at the surface. And that's going to equal the kinetic energy that it has when it's far away, okay? And what we can then say is that the change in the kinetic energy, if we just look at how the kinetic energy of this photon changes as we move it away from the surface, we find that that's equal to negative g times the mass. Now I'm going to come back to that because we don't have mass of a photon. We're going to make a substitution in a minute. Times the mass of the neutron star over r. Okay, where did that come from? Just a reminder, this was just the PE, because that is m lowercase g times h. And I'm going to put it in quotation marks. And we already saw today that this is GM over R squared. So if you plug all that back in, you get this expression. All right, that's why there's a single R in that denominator and it's not an R squared. So don't confuse that with the gravitational equation. All right, so what? What we're trying to determine is how the photon changes. For a photon, we don't really think of the kinetic energy of a given photon as 1/2 mv squared. That really won't work. So, you know, what we're thinking about is what is the energy of a photon? It won't work because, oops, photon. If we think about 1/2 mv squared, it doesn't work because of the two things we just thought about. It doesn't have mass and the speed is constant. So it would kind of seem like our photons would all have the same energy. Well, you probably remember something from chemistry, and that is for a photon that its kinetic energy can be expressed as Planck's constant h times the frequency of the photon. Does that look familiar? Sort of, maybe. What is this value? Anyone remember that? Planck's constant. You've used it, right?
Yeah. Yeah.
Okay, 6.26. I always have to look this one up. Nope, I'm wrong. 6.626. There's too many sixes in here. 6.626 times 10 to the minus 34 joule seconds. A joule is the unit of energy, right? And this character is, have you seen this before? You guys have to talk because I can't see your faces right now. Yes, no?
Yeah.
Is that frequency?
That's frequency. Okay, so this is frequency. The character is called nu. Okay, so that's like, it looks like a V that's been windswept. But you could put an F in there if you don't like that. And it's measured in hertz or in cycles per second, therefore energy comes out in joules. All right, this gets us somewhere. It get on the left side of the equation anyway, because then we can say it's the change in h nu equal to all this stuff on the right side, but we still have this annoying mass term in there, and we have to get rid of it. So to get rid of it, we're actually going to employ something else, which is what Einstein said about the equivalency of energy and mass. So Einstein's most famous equation is, come on, you know this one.
E equals mc squared.
Thank you. E equals mc squared. What's it mean? Well, it means that the energy is equivalent to the mass of whatever it is times the speed of light squared. So if we have a photon, then we can pretend that its mass is E over c squared. We've just learned that E is h nu. So for a photon, you can think of its kind of mass as being h nu over c squared. It's a little bit of a cheat. And in this case, we're thinking of it being on the surface. So that's h nu naught, if you want to put it like that, the initial frequency of the photon. So when I say frequency of the photon, photons do have a frequency. You know this because of chemistry also. Photons are different. If you're talking about visible photons, they're different colors, right, for different frequencies and wavelengths. So we're going to cast this into wavelength space eventually. All right, so I'm going to make my substitutions in this equation at this point. I'm going to, over here on the left, factor out the h because it's a constant, and just think of this as h times delta nu is equal to, and I can plug in place of the m, my h nu naught over c squared, and I get, I'm gonna just pull this stuff over to the left, gm all over r times h nu initial, the initial frequency of it, the frequency when it's on the surface of the neutron star, over c squared. All right, I'm getting somewhere now. I'm going to scroll this up a little bit. And let's pause before we push it any further and think about what this means. Change in frequency. We are talking about the before situation as a photon on the surface of the neutron star. We're talking about the after as being the photon far away, like arriving to our telescope. What does this thing I just highlighted mean is happening to the photon? What is happening to it on its travel?
It's like rotating speed is either increasing or decreasing.
Not rotating speed. What does the new mean?
Frequency.
Frequency. And that doesn't have to do with rotating speed. It has to do with what we're observing, the color of the light. So I know it does sound like when we talk about frequency before, we're thinking about rotating speed. But in this case, what the frequency means, it has to do with the wavelength of the light. So the frequency is changing. We're going to do a numeric example. I'm going to continue with this derivation and then we'll do a numeric example. It's really weird. So let's continue with the derivation and pull h delta nu. We're going to pull h nu naught over to that side. We're going to divide both sides by that. Because now notice Planck's constant divides out. And what we're left with is this kind of final equation. The change in frequency divided by the initial frequency is equal to negative gm over r c squared. By the way, the negative sign comes from some integration. All right, I know this doesn't say, you know, it might not jump out to you and speak very loudly, but let's look at it more deeply. And I'm also going to put it into wavelength space. So in wavelength, which is a little easier, I think, to think about if you're talking about photons, in wavelength space, the change in the wavelength, that's a lambda, over the initial wavelength, ends up being, because of the relationship between frequency and wavelength, this. And then because I cheated in deriving this equation and used just algebra, if you use real physics, real physics, it's not real physics, but it's general relativity and calculus, you get a factor of 2 in here. And then you usually get this equation that delta nu over nu naught is equal to negative 2gm over c squared r, okay? But what we're saying, because this is the lambda observed, like here on Earth, minus the wavelength initial at the surface of the photon, that's a little naught right there. It's the change, that's what delta lambda means. What we're saying is that the wavelength is going to get longer. That what we're seeing is something called gravitational redshift. It's crazy. It's basically that the neutron star is yanking so hard on these photons. It's not slowing them down, but it's making their very properties change. It's making their energies change. It's, as we know that already, right? It's making their wavelengths change. What we're observing is different from what's actually emitted. So let's try a numeric example of this, a real example. So example, suppose that we have a neutron star that has a mass that's about equal to the mass of the sun. Okay, so that symbol is M sub circle with a dot in it. That's one solar mass. And we know that that's 2 times 10 to the 30th kilograms. Okay, and that this star, this neutron star, has a radius of 7 kilometers, 7,000 meters. If light is emitted at a wavelength of 600 nanometers, which is a yellow-orange light. Okay, is what it would look like, yellowish orange. You could see it with your eye. At what wavelength would we observe it? Okay, that's our question, is what is the observed wavelength? So we have just about 1 minute left, so let me just plug in and show you how to do this kind of a calculation. Delta lambda over lambda naught is equal to, and I'm just plugging in the values, 2 times g, which is 6.67 times 10 to the minus 11, leaving off the units. 2 times 10 to the 30th kilograms over the speed of light squared, which is roughly 9 times 10 to the 16. Sorry, I omitted the speed of light is 3 times 10 to the 8 meters per second. And then this is in meters, 7,000 meters. Comes out that delta lambda over lambda naught is equal to 0.423, okay? So it's about 0.4 times the original wavelength. Well, our original wavelength is 600 nanometers, so if we multiply that out, we will get a value for delta lambda, and we find that plugging in delta lambda, as I said above, is equal to lambda observed minus lambda naught. That's going in up here for that, and you're multiplying. You find that if the delta lambda is 254 nanometers, then lambda observed is going to be a longer wavelength than before. Instead of 600, the observed wavelength is 854 nanometers. You don't have to change out of nanometers into meters because you have nanometers on the top and the bottom of the fraction here. All right, what does it mean? Again, it means the wavelength of that light is coming out at a longer place than when it started, and it means that that was emitted at yellow light that you could see. It is turned into infrared light on its way to your eyes. So the light that's coming out of pulsars is all being pushed to these longer wavelengths, and we're observing them in the radio band, in the infrared band. Okay, all right, that's all for today. I'm gonna stop my share and say goodbye to you. Thanks there. So have a great day and a great weekend, everyone. Tomorrow is our skip day.
Okay.